Recording progress means the recording started. I will check that I am sharing the right screen. Yeah. As I told you, there is a powerful tool for analyzing data. It's called eigenvectors and eigenvalues. And I explained you that when you have a picture, it's an example of data. Actually, the pixels of a picture are displayed in matrices. And when you distort the picture like this, you are distorting the pixels also. It's like transforming somehow, doing a transformation over that matrix. And there are some vectors that they don't change in direction during that transformation, and those guys are called eigenvector. And the reason is because the data is symmetric with respect to that. You'll be surprised that in engineering, when they are designing the bridges, for example, these bridges you cross, like Kaohsiung High, something, they have some sections like this. They have some sections in the shape of I. When you analyze the efforts and so on, they identify with these tools of linear algebra the axis, the principal axis, this one and this one. These are the eigenvectors of this section, and they mark where the efforts will concentrate, many other things. I mean, the data will be symmetric with respect to that, and also, of course, the center here. These sections, they survive some efforts. For example, when people cross, there are some momentums and so on. So it's important to know these distances. I mean, this is outside your scope, but you should know that these tools are also applied in engineering. They also apply in data analysis. They also apply in business, in economy, in whatever. So we will learn how to find those axes right now. We will use for that the properties of the matrices which we were teaching before. An eigenvector and an eigenvalue are defined as follows. You have a matrix A, you multiply by a vector. If that vector is an eigenvector, this product is equal to one value, one number, times the vector. So I give you one number. An example of that is the following. This matrix has one eigenvector. This is one eigenvector, and the eigenvalue is 6. How do you know that? Because I can multiply 6 times this and obtain this. And if I multiply the vector, the matrix by this vector, I obtain the same values. In other words, let's do it step by step. Eigenvector, matrix times eigenvector gives you an eigenvalue times the vector. So in this case, the matrix A is -6, 3, 4, 5. The matrix B is 1, 4. They claim normally in normal programs you have to find the eigenvectors. In this problem, they are giving you the eigenvector, but we'll learn how to calculate them. Now, if I multiply these two guys, I obtain this result, 624. This times this is 624. And if this is really an eigenvector, there should be a number such that when I multiply by the original vector, it gives me the same result. And that number is 6. 624. So we associate this number 6 to this vector. We say this eigenvector has an eigenvalue equal to 6. Proper values, proper vectors. There is another notation saying that. You can say eigenvalues or proper vector, vectores propios in español. Proper vectors, proper values, or eigenvalues, eigenvectors. How to find them? Of course, there is a mathematical operation, etc. But at the end, the result is this. Well, I will explain why this result is like that, because it's part of the completeness. of the section. If you want to solve this vector, let's assume you want to find this vector here. What do? You move to the left everything. Identity equals 0. Is what we have here, right? Now, if this matrix is invertible, I could find an inverse here, the inverse of this, A minus lambda I minus 1. This will become identity, and this will give me a vector equals 0. Well, I don't want a vector equals 0. This doesn't give me anything. So what I want is this combination to be non-invertible. I don't want it to have an inverse. So the condition for a matrix not to have inverse is the determinant of this matrix, this combination, is equal to 0. This is the condition we studied before. And this is the way how we calculate eigenvalues and eigenvectors. We take this operation, we calculate the determinant. I think I didn't explain how to calculate determinants, but I will explain that in simultaneity with this. For example, in that case, let's assume that we have the matrix, the original matrix they gave us was 6 minus 6, 3, 4, 5. And I want to find the eigenvalues lambda and the corresponding eigenvectors. Then I do this operation. This matrix minus lambda times the identity, minus lambda times the identity. This is the sum of matrices, this. So you will obtain minus 6 plus lambda, 3, 4, 5 minus lambda. And you will calculate the determinant of this. The determinant, this can be calculated in the software, but the determinant is the product this times this minus 4 times 3. So at the end, you find an equation, quadratic. And you find two values, minus 7 and 6. Now, the software I showed you before, it calculates directly the eigenvalues for you. If you tell to a software, give me the eigenvalues of this matrix, immediately will give you minus 6, minus 7, 6. But I am explaining this is for you to know what does it mean. Because the important thing is not to know how to calculate. The important is to understand the meaning of the things. That's the most important. Actually, there is a secret among physicists and mathematicians. In most of the cases, when we start to study something, we don't know how to calculate the things, but we understand. We have an understanding. And then after is when we try and then we find the way, no? Okay? So the most important is to understand the process, to understand. Example, let's go to a specific example, maybe this one. This matrix, I want to calculate the eigenvalues and eigenvectors. I will do it completely. This is a 3 times 3, so it's not trivial to find the eigenvalues and eigenvectors. In 2 times 2 was trivial. Then in that case, you use this equation. We already know that the condition is this, determinant of the matrix minus lambda times the identity. This is what they do. The matrix minus lambda. So it was 2 minus lambda, the first. 0 minus 0, because lambda times 0 is 0, gives 0. 0 minus 0, 0. 0 minus 0, 0. 4 minus lambda, 4 minus lambda. 5 minus 0, 5. 0 minus 0, 0. 4 minus 0, 4. 3 minus lambda Lambda times 1 is lambda, gives you 3 minus lambda. Then you have to find the determinant of this. This determinant you can find in the software. Or you can tell you to the software since the beginning, give me the eigenvalues and give me the eigenvectors of this. The software can do it. It can do it. You don't have to calculate step by step these things. At the end, when you calculate the determinant of this, you obtain this equation for lambda, and you find 3. It's a cubic equation. You obtain the eigenvalues minus 1, 2, and 8. But once you obtain the eigenvalues, you want to know the vectors associated to those values. What do you mean by the vectors? The vectors means that if I have this condition, and this is an eigenvector, this is the original condition, and this value, the first value, is minus 1. So it means that there must be a vector such that this condition is true. I replace minus 1 here. And that's what I want to find now. And I know A. A is the matrix given here, which is 2, the original matrix, 2, 0, 0, 0, 4, 5, 0, 4, 3. This was the original matrix. So I put this matrix here, and I work with this equation. I want to find the values of this. And this has 3 components. 3 components. How do I know? Because the matrix is 3 times 3. I have 2, 0, 0, 0, 4, 5, 0, 4, 3. The eigenvector I can represent explicitly as x, y, z equal the eigenvalue lambda is minus 1. I want to find the vector associated to minus 1 to the first eigenvalue, and that vector is x, y, z. So I want to solve, I want to find x, I want to find y, I want to z. I have 3 equations, 1 equation, 2 equations, 3 equations with 3 unknowns. In most of the cases, I have to assume by answer to one value. The software will give you a minimalistic approach. These are the equations. Can you see? 2 times x equal minus x. It's the same. It's what I am showing here. It's exactly this. So the equation at the end is this for the eigenvalue minus 1. 2x, 0 times y is 0, 0 times c is 0. So at the end, it's only 2x on the left. Equal to minus x. This is the first equation. Second equation, 0 times x is 0, 4 times y is 4y, 5 times c, 5c, equal to minus y. The third equation is 0 times x is 0, there is no x there. 4 times y is 4y, 3 times c is 3c, minus c on the right-hand side. These 3 equations, you have 3 equations. So the first result is telling you that x is 0. You move x to the right left, is 3x equals 0. So x is 0. That's why the first component, of the vector, that's why the first component is 0. Here. This is the first component of the vector. Let's put it like this. So if x is 0, the first component of the vector is 0. X, this one, equals 0. This one equals 0. Second component, we have to find y and z. So we find that y is equal to minus c here when you solve. And the third equation is redundant. It's telling you that y is equal to minus c also. This redundancy in equations is expected because we impose the condition determinant equals 0. Remember, when the determinant of a matrix is 0, there are redundant rows, redundant columns. So that's expected. So in any case, the only thing you know is that the second component and the third component are negative of each other. So you said arbitrarily. They selected y equal 1. If y is equal 1, c is minus 1. This is one possible eigenvector. But I could have put here 8, a minus a.